Okay, so last thing we need to do in Unit 16 is we need to put it all together. What we've been building towards is collecting a bunch of information about our functions so we can hopefully sketch an accurate graph of our function. So what the questions are going to ask you to do is find all of this information that you see listed here. Find the domain, find the asymptotes, find the intercepts, find the turning points, find the intervals of increase and decrease. And you're probably going to do these two at the same time because, well, you can use your interval table here to check for local maximum and minimum, and find the points of inflection and the intervals of concavity. Again, you do those at the same time because you can use that interval table to check if you actually have a point of inflection. And then the last thing is you might want to find the values of any points that are easy to calculate. So if you haven't figured out where x, what point you have at x equals 0, you would figure that out last. So let's just go through an example here. We're given a function, y equals x over x squared minus 4. And we're also supplied with the first derivative and the second derivative because at this point we just want to compile our information and sketch the graph. And we sort of assume that you already know how to take these derivatives. Okay. So let's see, where do we want to start? Number one was our domain. So we want to look at our function, f at x. Okay, and what's our domain of this function? Well, as with every function that we've encountered, it has to be an element, x has to be an element of a real number. Are there any restrictions on this function? Yes, what are they? X cannot equal plus or minus 2. Now, don't worry too much about the restrictions. Okay? If you don't get the restrictions at the very beginning, usually they pop up later in the question. You find them, and you can go back and you can add them in. Number 2 was the asymptotes. Okay. So we'll do our vertical asymptote first, which, if you remember, involved taking our denominator of our function and setting it equal to 0. So our denominator is x squared minus 4. We set that equal to 0, and we solve for x. So I can factor my left-hand side, and I get x equals positive 2, x equals negative 2. Those are going to be the equations of my vertical asymptotes, which you'll notice these are the two restrictions that we had placed on our domain because the function isn't defined at the vertical asymptotes. Our horizontal asymptote here. Well, we want to look at what is our highest power of x. It's x squared, and we want to take the limit as x goes to positive or negative infinity of our function where we're dividing through by that highest power of x. So we'll have x over x squared in our numerator, x squared over x squared in our denominator, and we'll subtract off 4 divided by x squared. We can simplify this limit as we go to plus or minus, as x goes to plus or minus infinity of our numerator is 1 over x. Our denominator is going to be 1 minus 4 over x squared. And what we remember is that as we take our limit, as x gets very, very large and very, very small, all terms that are some number divided by x or x squared or x cubed go to 0. So we're going to be left with 0 divided by 1 minus 0, or just 0. So our horizontal asymptote is y equals 0. Okay. Step 3 here is our intercepts. Okay. We want our x-intercepts and we want our y-intercepts. So our y-intercepts occur where x equals 0. So we sub x equals 0 into our function, and we get, oh, we just get 0. Let's say f at 0 equals 0. So we've got 0, 0 as our y-intercept. That's also going to be our x-intercept. Okay. Well, the x-intercept would be where y equals 0. So we would set the numerator equal to 0. So our numerator here is just x. So again, x equals 0. This is numerator equal to 0. Okay. So 0, 0 is both our x-intercept and our y-intercept. So now we're on to 4, 5. We're looking for turning points. Slash our intervals of increase and decrease. Intervals of increase slash decrease. Okay? It's a lot of slashes in one line, but you get what I mean. So, turning points, we want to find our critical numbers. So we're looking for where our derivative, first derivative, equals 0, or where our first derivative does not exist. So for where the first derivative equals 0, we take the numerator of the first derivative and we set it equal to 0. So let's see, the first derivative was listed up at the top of the page. That was negative x squared minus 4 in our numerator. And we want to solve for x here. So we get x squared equals negative 4, which we cannot solve. So we'll just say no solution. Where does our second derivative not exist? Well, we want to take the denominator of our first derivative. Sorry. Where does our first derivative not exist? We take the denominator of the first derivative and we set it equal to 0. So our denominator is x squared minus 4 all squared. Set that equal to 0, which is going to solve to give us positive and negative 2. Now, do these points represent possible turning points? They don't, because we've already encountered these already. We already know that these 2 points here are vertical asymptotes. Okay? So these cannot be turning points if they're vertical asymptotes. So we can say that we have no turning points. Even though negative 2 and positive 2 are not possible turning points, they're not local max or min, we're still going to include them when we do our interval table. Because even though they're not turning points, they are still places where the curve can change from increasing to decreasing or vice versa. So let's set up our interval table. And our intervals are just going to be negative infinity to negative 2, negative 2 to positive 2, and positive 2 to positive infinity. We want to check the sign of our first derivative. So we list our terms in our first derivative. That's our numerator, our denominator, x squared minus 4 all squared. And we're trying to figure out the sign of our first derivative here. So the second one here is easy. It's always going to be positive. Our first one, let's see. Anything we put in for x is going to be positive. The negative will make it negative. So a negative minus a negative is always going to be negative. So this one is going to be negative everywhere. So our first derivative is always negative. What does that tell us about our function? Well, it's going to be decreasing, decreasing, decreasing. So it's always decreasing. So this is consistent with the fact that we don't have any turning points. If our function is always decreasing, it never changes from increasing to decreasing or vice versa, so we don't have any turning points.
That last one would be positive. Because if you take, like, say, 2, it's always negative or something.
But the negative sign will make it negative. Yeah. Okay. So 6 and 7, we want to check points of inflection and concavity. So what we're doing here is basically the same thing we did with our first derivative, except now we're doing it with our second derivative. We are looking for where our second derivative equals 0 or our second derivative does not exist. So let's see, we've got our second derivative listed up at the top of the page. We want to see where the numerator is equal to 0. So 2x x squared plus 12 equals 0. And what are we going to get for solutions here? X equals 0 is one solution. And another possible solution would be x squared equals negative 12, but that doesn't work. What about places where our second derivative doesn't exist? Well, let's take our denominator and set it equal to 0. So x squared minus 4 cubed equals 0. And if we solve this, this is just going to give us our old friends x equals positive 2 and negative 2 again. Okay? So this is telling us that the concavity, like these are possible places where the concavity can change. So the concavity can change at those vertical asymptotes as well. Yeah?
If you find an asymptote in the first function and then the first derivative, would it be the same for every other function?
Yeah, it's likely going to occur everywhere. Okay, because in these ones here, this is because these are rational functions, and we're always going to have that quotient in the bottom, which just increases, like we square it every time we take a derivative. So it's going to appear everywhere down.
So okay, you don't even have to factor it out.
It's good form to show explicitly what you're doing here. Okay, just so you know. And I mean, I'm doing this every time to make sure that I'm going to take these numbers from here, and I'm going to use them to define my intervals. So I don't want to forget to put those numbers in my interval table, which is why I'm doing it every time. Okay. So let's set up our interval table here. Our intervals are going to be negative infinity to negative 2, negative 2 to 0, 0 to positive 2, and then positive 2 to positive infinity. And again, we are checking the sign of the second derivative. So I've got a 2x, I've got an x squared plus 12, and I've got my denominator, x squared minus 4, all cubed. And I want to figure out what my second derivative is doing. So let's see. We're going to have negative, negative, positive, positive, positive everywhere because the x is squared. And here we are going to have positive, negative, negative, positive. So what does this tell us for our function? Second derivative is negative. This is going to be concave down. Positive, it's going to be concave up, then concave down, and then concave up. Okay. So do we have any points of inflection? Well, we know that negative 2 and positive 2 are our vertical asymptotes. So we do have one point of inflection right here. That was our x equals 0, okay, at our point 0, 0. Okay. So now we can put all of this information together and sketch our graph. So we've got a set of axes here. We've got an intercept at 0, 0. At, let's see, we had two vertical asymptotes here. So let's put those in as dashed lines here. So we had one here and one here. These are x equals -2, x equals 2. We had a horizontal asymptote at y equals 0. And we can also use this information that we had in our tables. Okay? We know that our function is decreasing everywhere. So we can sort of divide this into 1, 2, 3, 4 regions. Here we know that it is decreasing. It's decreasing here. It's decreasing there. And it's decreasing over here. In terms of a concavity, we know that it is concave down, concave up, concave down, and then concave up. So if our function is decreasing and concave down, it's got to look something like this. Okay? So it decreases as we go from left to right. We've got to map it onto our horizontal asymptote there. If it's going to be decreasing and concave up, it's got to look something like this. It hits our point of inflection and our intercept and continues on down like that. And in our last segment here, it is decreasing and concave up. It's got to look like that. And it's got to meet up with our horizontal asymptote at very, very large values of x. So that is going to be the sketch of our function.